right, so we so far have learned a little bit about the definite integral from a to b of f of x dx. And you should recall that this represents, if f is non-negative, the area bounded by f in the x-axis from x equals a to x equals b. And if f can be negative, then it represents the net signed area bounded between the function f and the x-axis from x equals a to x equals b. In other words, if f can be negative, then we take the area that's above the horizontal axis and subtract from it the area that's below the horizontal axis. And so far for working out the values, a value of a definite integral, all we've been doing is geometry. If we wanted to find an exact value. So I gave you some examples in the last section where the functions that you're finding the area bounded by and so forth were linear, which then just required you to find the area of the triangle or the rectangle or whatever it was. And if part of it lie below the x-axis, then you take the area that's below and subtract it from the area above, those sorts of things. Or the semicircular example where you just found the area of the semicircle. So again, we were relying solely on geometry because of the particular function that was in the integrand was something that could be handled with geometry. The only other alternative that we really have at our disposal would be to approximate the area, assuming that the area is curved, or the region bounding the area is curved, that we would approximate the area using either rectangles or trapezoids like we did at the start of this section as a reminder of something you did in the pre-cal class. All of that's something that we should be able to do. But there's another way of evaluating an integral, a definite integral, and so we want to work that out here a little bit. Now, to work this out, I'm going to go first by an example, okay? So let's consider the velocity function here. Let's let v of t be equal to 2t plus 3. I guess we can call this example number 1. And this is for t greater than or equal to 0, just to make things pretty straightforward. So what I want you to do is let's find the displacement of the object moving with this velocity on the interval from 1 to 5. Now, I would like you to pause the video and give that a shot. So I would assume, if you've been following along closely and knowing what's going on, that you should be able to work this out without too much of a difficult time. So pausing the video and practicing to make sure you can would be great. Now, if you're absolutely stuck, let me give you a hint. Pause the video now if you don't want the hint. But the hint would be to go ahead and draw the picture and find the area bounded by the curve. So I'm going to set that up here. So essentially what we're doing for this is we're looking at the integral from 1 to 5 of 2t plus 3 with respect to t. Graphically, and I'm not going to try to draw an accurate picture, I'm just going to do a quick sketch. So graphically, we're looking at finding this area here. Let's shade it right through here. Now, that represents also the total distance traveled by the object, because the velocity is non-negative, but I'm using the word displacement here intentionally because of some other ideas it should conjure up in the moment. Okay. All right, so how do we find this this displacement, this area bounded by the curve? Well, I know I didn't draw this perfectly straight, but this is a straight side here. These sides are parallel, these two vertical sides. And so we have a trapezoid happening here. So if I just find the area of the trapezoid, then I have the displacement traveled. If I plug 1 in for t to get this side right here, we get 5. If I plug 5 in, we get 13. So that's this base over here. And then the height is this length, this perpendicular side, 5 minus 1, or 4. And so this, again, is going to be just the area of the trapezoid. So this is going to be 5 plus 13 times the height 4 divided by 2, which is just 18 times 4 over 2, or just 9 times 4, which is 36, or 18 times 2, however you want to look at it. So that means that the object traveled, or 36 units. I didn't give any distance units yet in the example. It's 36 units from where it started. And so it could be 36 feet, miles, kilometers, inches, centimeters. It doesn't really matter. It also means that the object traveled a total distance of 36 units, whatever the units are. So I'm trying to build a connection to this. So I want to go for a second and ask about the concept, ask you to recall the concept of displacement. So if it's going, let me actually erase that for a moment. Think of the function s of t as the position function of this object. Then we said a while back that the displacement on the interval from A to B is given by S of B minus S of A. So, well, wait a second here. If my displacement was 36 that we found here, and I know the velocity function is 2t plus 3, we should be able to find the position function by taking an antiderivative. So if v of t, again, is 2t plus 3, then the position function is going to be, let's reverse the power rule here. So we're going to add 1 to the exponent. There's already a 1 here. So let's add 1 to make it a 2 and divide by that 2. So that becomes a t squared. Antiderivative of 3 is going to be 3t. And then we're going to have plus a constant. I don't have any information at the moment to figure out what that constant actually is, but that doesn't matter. I'm still doing okay. So we wanted the displacement of the object from 1 to 5. So that means if I would calculate s of 5 minus s of 1, I should get the displacement of the object. So if I plug in 5, I get 5 squared, which is 25, plus 3 times 5, which is 15, plus whatever c happens to be. Minus, if I plug in 1, I get 1 squared, which is 1, plus 3 times 1, which is 3, plus c. And so what is this? This becomes 40 plus c minus 4 minus c when I distribute the negative, and 36, which is, my screen doesn't want to scroll for me, which is exactly what we found up here. That's kind of amazing. Or coincidence? Well, I think not. Well, what did we just learn here? We just took the integral from 1 to 5 of the velocity function v of t, and found that the area that we found there was exactly the same as taking the position function at 5 and subtracting from it the position function at 1, or finding the displacement. This is actually not a coincidence at all, as you would probably have guessed already, but this is a very important theorem, which in this section we're going to call the evaluation theorem. I don't know what I just did to my screen, so hold on for a moment. This is called the evaluation theorem. And I'm going to have to pause this. This is called the evaluation theorem in this section. Sorry, I was interrupted in making the video. And so I don't know exactly where I was in my sentence before I stopped. But nonetheless, we're going to call this in section 5.3 the evaluation theorem, but we are going to change the name of it in section 5.4. That's just the way the book does it, and I am following that pattern here. Okay, so the evaluation theorem says, and this is going to help us evaluate definite integrals without having to do any geometry. But the geometry is still helpful, so you're still going to want that as a tool in your toolkit. Okay, something that is useful in many situations, because sometimes the process that I'm going to describe right now in the evaluation theorem is much more complicated than doing the geometry. So, if f is continuous on the interval, it's the closed interval, a, b, then the definite integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of lowercase f. Or in other words, that means if I take the derivative of capital F, I get lowercase f. Now, this is a really powerful theorem. Okay, so as long as we have the function being continuous, that's something that we talked about before. You have to check to make sure the function is continuous on that closed interval AB. Then we're going to take an antiderivative of lowercase f, find an antiderivative of lowercase f, and then you're going to plug in b, the upper limit of integration. You're going to plug in a, and then you're going to subtract the two, and that's going to give you the value of that definite integral. Now, remember, up here, I used C in my determination or in finding my antiderivative of S. I was finding the most general antiderivative, but the C here and here in this expression, they ended up canceling with each other because, the distributive of the subtraction that's going on and the distributive of that minus sign causes C to go away. So C is irrelevant to us. We don't need the most general antiderivative. We just need an antiderivative, and this will work out. So as part of the evaluation theorem, again, we just need capital F to be any antiderivative. All right, let's get some practice with this. All right, so I want you to evaluate the following. Now, ideally, right now, you pause the video and you go try these things out and then come back and see how well you did. That way, if you really are understanding what I'm talking about. If you just watch me do it, then how do you know whether or not you can do it on your own? You really don't. So please pause the video and go give this a try without me. All right, so x to the negative 2, got to be careful because x to the negative 2 means it's 1 over x squared, and we need our function to be continuous on the closed interval from 1 to 4. And it is, because the only discontinuity of 1 over x squared is at 0, and so 0 is not included from 1 to 4. So we're okay here. But it's worth checking to make sure the function is continuous. And so what do I do? Well, partly what I have to do is show you some notation here. So we need to find an antiderivative of x to the negative 2, which means I'm going to work on reversing the power rule. So I'm going to add 1 to the negative 2 to make it negative 1, and then divide by that negative 1. So it's going to be negative x to the negative 1. I know I said divide by negative 1, and I put it as a multiplier, but that's still the same thing. And then I need to plug in 1 and 4 and subtract. But let me show you some notation here. When we have a single expression like this, or single term in our expression, we put the antiderivative there, then we put a vertical bar next to it. And then we put our limits of integration in the same order. The 1 was on the lower limit, so it goes on the bottom, and 4 is on the top, upper limit, so it goes on the top like this. What this means is that you're going to plug in 4 for x, and then you're going to plug in 1 for x, and then you're going to subtract. So that's the special notation for this. So this is going to be, now remember, with the negative exponent here, that means that's in the denominator. So when I plug in 4, it's really negative 1/4 minus, and if I plug in 1, it's negative 1/1, so negative 1, like this. And so this works out to be 3/4. All right. Now's a good time to pause and go do B if you haven't done it yet. All right, so for B, I'm going to do the same process. I'm going to find an antiderivative. Now, just as a side note, this one here is one that you could easily draw and do the geometry of, but let's practice our evaluation theorem. So antiderivative of negative 3x is going to be negative 3 over 2x squared. Reversing the power rule, so you're going to add 1 to the exponent, divide by that new exponent, and then plus 5x. Now, similar to what we did over here with that vertical bar, we want to put some notation to this so that we know that the reader knows we still have some work to do. And since we have a sum here, this is what we tend to do. Instead of using a, we tend to use, instead of a vertical bar, because of the sum that's going on here, we tend to use brackets so that the reader knows that the negative 2 gets plugged into both terms, as does the 1. So I'm going to plug in 1 to both terms in the expression, plug in 2 into both terms in the expression, and then subtract. If I just use the vertical bar, it's a little ambiguous, and someone might think, are we only plugging this into the 5x, or do I plug it into the negative 3 halves x squared term as well? It might become confusing to some. So we put brackets around sums and differences. So if I plug in 1 squared, of course, is 1, so I get negative 3 halves plus 5 minus, and if I plug in negative 2, I'm going to do some of this mentally here. Negative 2 squared is 4, and then 2 goes into 4 twice, so this becomes negative 6. And why am I plugging negative 2 in first? No, I'm sorry. Wow, I almost misspoke. I'm got too many things in my mind. Never mind. Forget what I was just about to say. Plug in negative 2 into to that term, I get negative 6. Plug negative 2 into here, we get negative 10. Like this. And then do some arithmetic. So this becomes, what is it? Negative 7 halves minus 16. No, minus negative 16, excuse me. And so 16 plus 7 halves is 19 halves. So 7 halves is 3.5 or 3.5, and so that works out to be 19 halves. Apologize, I got some distractions while I'm making this video, so I'm just trying to concentrate. Again, if you haven't tried part C yet, go try part C before you see what I do to it. See how well you understand what's going on. All right, so the only discontinuity that happens here is at 0. 0 is not in the interval from 1 to 9, so I can go ahead and apply the evaluation theorem. And so I need to find an antiderivative of 1 over root x. Some of you might not see what that is at the moment, so maybe a rewrite would help. You can rewrite this as x to the negative 1/2, and then you can reverse the power rule. So if we're reversing the power rule, then I'm going to add 1 to get a positive 1/2 to that exponent, and then I have to divide by 1/2. Dividing by 1/2 is the same as multiplying by 2, so this is 2x to the 1/2, evaluated from 1 to 9. So we're going to plug 9 in, so it's 2 times the square root of 9 minus 2 times the square root of 1. Square root of 9 is 3 times 2 is 6 minus 2, and this works out to be 4. Now in examples A and C, the geometry of it, those graphs are curved, so you wouldn't be able to, you don't have any formula for those curves for finding their area. And so this is the way that you would have to find the exact area. The only other way you would be able to come up with an answer that's reasonable is to look at the approximation using the rectangles. And if you wanted to let the rectangles get out to higher and higher numbers, you could probably see that in part A, the answer is approaching 3/4, and in part C, it's approaching 4. Um, but that could be a lot more work than this evaluation theorem, which is very fast. In part B, again, you could draw that picture and find the area and with geometry and get the same answer as 19 halves. It might have actually saved you a little bit of time than all this work here, but this works. All right. In part D, if you haven't tried it, please go try it. All right, so I need an antiderivative of cosine of theta. Well, sine of theta is an antiderivative. I don't need the constant of integration of this one. I need to evaluate this from pi to 2 pi. So I'm going to get the sine of 2 pi minus the sine of pi. And if you know, both of those are 0, and so this works out to be 0, and the auto correct is making the zeros look more perfect. I don't think maybe an illustration of why that comes out to be 0 might be useful right here. Let me see if I can do a halfway decent graph of the cosine function real quick. So the cosine function looks like this. And that is a halfway decent function, or picture of the function. Cosine equals 0 at pi over 2 and 3 pi over 2, which are these two values here. And, I just drew one cycle. That's at 2 pi. That's at 0. Pi is right here in the middle, like this. And so what we're doing here is we're finding the area bounded from pi to 2 pi. So this area I'm sorry, I misspoke a little bit. We're finding the net signed area between pi and 2 pi if we look at the graph. And I did actually a pretty good job here. This area here and this area here are exactly the same, but the one below is counted as negative and the one above is counted as positive. And so they're going to cancel each other out. And that's why we end up with 0 as the answer to this one. I'm going to pause the video, write some more practice examples down, and then I'll restart in a moment. All right, here are a few more to try. I am kicking up the level a little bit. I do want to make them a little bit more complicated for you so that you have to think, God forbid. And hopefully it comes back to this process. I think you got a little bit of Julia barking there. All right, so again, I was interrupted in making this video, so I don't know what the last thing I said was. These are getting slightly bit more complicated in some regards, so give them a shot. Be careful. Remember that in section 5.2, I said that there were no rules for rewriting multiplication or division for integrals. Okay, we can rewrite a sum or a difference as the sum or difference of integrals. Constant multiple, we can move a constant multiple out, but product or quotient of two functions doesn't have a special rule. So keep that in mind as you work these out. So pause the video and go try to solve these. Again, hopefully you try to solve them. Now, I'm going to go ahead and start working these things out. 8 here is a constant multiple, so we can rewrite this as 8 times the integral from the natural log of 3 to the natural log of 6. Whoops. Natural log of 6 times e to the x, or of e to the x dx. And then we should know the antiderivative of e to the x is just itself, e to the x. So this is going to be 8 times e to the x evaluated from the natural log of 3 to the natural log of 6. And then when I plug in, it's going to be 8 times e to the natural log of 6 minus e to the natural log of 3. And the nice thing is that e and the natural log are going to cancel with each other here. This is just going to be 8 times 6 minus 3, and that's just 24. All right, so in letter F, I know this one might be a little bit confusing for some and might be a little bit of a challenge, and that's okay. What we want to do is we want to rewrite the algebra first. We want to sharpen the axe before we get into going ahead and trying to find an antiderivative. Now, remember now that x squared and its cube root is really x to the 2/3. Okay, if you forgot that, so be it, but it is. And then from there, we can separate the fraction into two separate fractions and write this as, the definite integral from 1 to 8. And then we can look at the terms separately. X over x to the 2/3. That right there is going to work out to be x to the 1/3. Because remember, we're subtracting exponents, and there's a little invisible 1 on this x. So 1 minus 2/3 is 1/3. Minus, and then this is just going to be 1 over x to the 2/3, or x to the negative 2/3. And then all with respect to x. And so when we go to work out the antiderivative of this, we'll add 1 to the exponent. So 1/3 plus 1 is going to be 1 1/3, or 4/3. And then we got to divide by 4/3, but that's the same thing as multiplying by 3/4. So 3/4 x to the 4/3 minus, when I add 1 to this term here, I'm going to get positive 1/3, and I got to divide by 1/3, so it's going to be multiplying by 3. And then I need to evaluate this from 1 to 8. Now, if I plug in 8, so remember the fractional exponent with a 3 in the denominator means you're taking a cube root, and I would do that first. The cube root of 8 is 2. 2 to the 4th is 16. So this is going to be 3/4 times 16. And then if I plug in the 8 here, I get 3 times 2 is 6, so minus 6. And then going to go back and plug in 1, but that's going to be easy because that's just going to be 3/4 minus 3. And then the rest is just arithmetic. So what is that? 12 minus 6 over here minus, you could think of this as 12/4, and 3 minus 12/4 is negative 9/4. And then so it's 6 plus 9/4. And however you want to think about this, that's 24/4, 33/4 as that. All right, keep getting interrupted a little bit, but that's okay. Moving on to these last two here. G should be fairly straightforward. Again, please, you should be trying these on your own before looking at my work. 3/2 x squared is an antiderivative of 3x. E to the x is its own antiderivative. And then we have to evaluate from negative 2 to 1. And so if I plug in 1, we get 3/2 minus e. And then if I plug in negative 2, I'm going to get 4 divided by 2 is 2 times 3 is 6 minus e to the negative 2. And there's not much to simplify there. Of course, 3/2 minus 6 is something you can simplify, but can't subtract the e parts of it, so I'm not even going to bother. Then be careful with letter H. Again, there's no product rewrite for an integral, so you don't want to just go right in and try to separate this. You don't want to separate this is an integral from 0 to 1 of u times integral from 0 to 1 of root u and u to the 1/3. Do some algebra here first, okay? So we are going to leave this as an integral. But I'm going to distribute the u, and so I'm going to end up with u to the 3/2 plus u to the 4/3, okay? And then evaluate that with respect to u. Now again, we still got to find an antiderivative. So antiderivative of u to the 3/2 becomes u to the 5/2 divided by 5/2, or 2/5 u to the 5/2 plus, this is going to become, going to add 3/3 here, so that's 7/3 with 3/7 u to the 7/3 evaluated from 0 to 1. And then if I plug in 1, I get 2/5 plus 3/7. Plug in 0, I get 0, which is nice. And so then just find your common denominator and work that out further if you want, or don't. It doesn't really matter. All right, I'm going to stop the video here. There's more to this section, but I'm going to do that in a separate video.